Hello, welcome back. In our previous video, we went through one specific technique of integration called substitution. This video, we are going to be focusing on one other technique of integration, and then sort of an introduction to looking up formulas on a table. So the main technique of integration that we're going to focus on is integration by parts. And I'm going to follow along with your handout that you have, but I just don't have the room that I need. So I'm going to do all these problems on a separate sheet here, and I'm going to rewrite our integration by parts. Integration by parts. And it basically looks like this. And normally I show where all this comes from. It's basically, if you remember from last chapter, the product rule, where there were multiplies and derivatives and things like that. And so this would be taking all that and rearranging it and then doing the opposite. And so this is sort of the product rule backwards for integration. The tricky part is going to be trying to figure out what is the u and what is the dv. And that's going to really be sort of the conundrum here. And there's a saying, and I've changed it a bit from my engineering calculus to business calculus. The main thing we're going to be looking for, and let's make this a bold color, is going to be L, then A, then E. And that is going to stand for logarithms algebra and exponents. Meaning, we're going to look, are there any logarithms as a part of it? That's going to be our u. So this is going to be our, let's go here. Let u equal. And then whatever's left is going to be our dv. So we're going to start with logarithms. If there's a logarithm, that's going to be my u. If there's no logarithms, then is there any algebra? And when we say algebra, what we mean is like x squared, x to the third, x, like a polynomial that's going to be there. And then if there's no algebra, then we look for exponents. Now, it's very possible that u is going to be the only function in the integral. But this is going to be sort of our strategy as we're moving forward. And let's start with our first problem. This is the integral of 3x e to the x dx. And I'm going to notice that I have some algebra here, meaning the 3x. So I'm going to go off to the side here, and I'm going to let my u be my 3x, which means my dv is going to be my e to the x dx. It has to include the infinitesimal, meaning the dx. As far so if there's a d something, it has to equal some function and then a d something. Now you'll notice in my integration by parts that I have a u, a v, a du, and a dv. So right now I'm only given the u, so I need a du. So I'm going to take the derivative of that. That's just going to be 3 dx. And I have a dv, which means I need v from that, so I need to integrate that. And we're not going to worry about the plus c yet. We will get to that. That will come towards the end here. And now I'm going to put all this together where I need v times u. So this is going to be 3x e to the x. So there's my uv minus the integral of v du. And there I'm going to put my plus c. And I'm hoping that this has made my integral easier. And it actually has. I'm going to pull that 3 out. Now the only integral I have in here is the integral of e to the x, which I know is a very easy one. And this answer is perfectly fine. However, I have seen some textbooks rewrite it like this. Either is fine. One is not more or less correct than the other. The second one is useful if we have something else calculus-wise to do with it. Otherwise, the top one is just fine. It's not, again, one is not more correct than the other. All right, let's try another one. Number 2. This one's very similar. And once again, I have no logarithms, but I do have algebra. I have a 5x, or 5 times x. So I'm going to let u be my 5x, and my dv is going to be what's left. That's going to be e to the 7x dx. Now I need du, so I'm going to take the derivative. I'm going to get 5 dx. And I need v, which is the integral. Now, I need to go off to the side here. The integral of e to the 7x, I need to do a substitution, and I'm going to let t instead of u, because there's too many u's here. So I'm going to let t be 7x, which means dt is 7 dx. So my dx gets an extra 1/7 when I integrate it. Which means what I have here is I end up with 1/7 e to the 7x. So we get that extra 1/7 because that's e to the 7x, meaning e to the ax is going to give me, when I integrate it, 1 over a times e to the ax every time. So let's go back. Now we're going to do u times v. That's going to be 5 over 7x e to the 7x minus v, which is 1/7 du. So that's going to be actually 5/7 integral of e to the 7x plus c. And very nicely for us, we're going to integrate. Now, we're going to get an extra 1/7 again when I integrate the e to the 7x. So we're going to get another 7. So this is going to become 5 over 49. 7 times 7, e to the 7x plus c. And again, we get that extra 7 for the same reason off to the side that I did that integral of e to the 7x. So every time we integrate that e to the 7x, we're going to get that extra 1/7 as a part of it. All right. Next up, number 3. The integral of the natural log of 2x minus 8 dx. Now, in this case, I only have one function, so there's no guesswork here. And dv is just dx. Nowhere else to go with that. Now, our du, when I take the derivative, that's going to give me 1 over 2x minus 8. And then chain rule says times 2. So make sure that we have that extra 2 in there. In fact, I'm going to actually rewrite that up top here. Also, when I integrate, the integral of v equals dx is just going to be x. The integral of dx is just x. So I end up with u times v. So this is going to be x ln of 2x minus 8 minus the integral of v du. I'm going to pull that 2 out. Now we're going to run into a slight snag here. I'm going to do my work off to the side here. I'm actually going to do some long division to see what I get. So I'm going to go 2 times, oops, actually, I need something times 2x to give me x. That's going to be 1/2. That's going to give me x minus 4. Give me a remainder of 4, which means this becomes x natural log of 2x minus 8 minus 2. And this becomes the integral of 1/2 plus 4 over 2x minus 8 dx. Now, we need to keep in mind that this now becomes a couple of integrals. So this becomes x ln 2x minus 8 minus the integral of dx minus, I'm going to pull a 4 times 2, that's going to be 8 out in front, the integral of 1 over 2x minus 8 dx plus c. All right, we're going to keep this as simple as we can. Now, the integral of dx is just x. Now, the integral of 1 over 2x minus 8, if you remember, that becomes the natural log of 2x minus 8 times an extra 1/2 because of that 2 in front. We did that a little bit earlier in the previous video. So I will show it here real quick. So let me just demonstrate that off to the side here. So the integral 2x minus 8 dx, I'm going to let t be 2x minus 8. Again, I'm using t instead of u because we already have u's going on here. It's going to get confusing. So there's my extra 1/2 that you can see I'm going to get there. This becomes 1/2 integral of 1 over t dt. So there's that extra 1/2 that you see there. So this becomes x ln 2x minus 8 minus x. That the 8 gets cut in half, so that becomes minus 4 ln of 2x minus 8. That, all of that, and actually, I should be clear, these should be absolute values. And all of that is our answer for number 3. So a couple new things that we did long division with this because we had the same degree over the same degree. There's another way to do that where you do some factoring and things like that, where we could make that a little bit simpler, but this is the way I prefer doing it. All right, so we are on to number 5. And then in addition to that, we need to remember that extra 1/2 because of the integral of 1 over 2x minus 8, we get that extra 1/2 in there. All right, number 4. Oops. Number 4. Here we have a definite integral. And what do we let u be? Well, if we remember when we go back, we're going to use our logarithm. So that's going to be our first choice. On occasion, that won't work, but we'll know right away if it doesn't work. So I'm going to let u be ln of t, which means dv is 7t squared dt. So du becomes 1 over t dt. And v, when I integrate that, I get a 1/3, so that becomes 7/3 t to the 3rd power. So this becomes integral from 1 to e, I'm sorry, uv So this becomes 7/3 t cubed ln of t from 1 to e minus the integral of 7/3 of, I pulled the 7/3 out. That's going to be t cubed times 1 over t dt. And there's no plus c on this one because it's a definite integral. So we're going to evaluate these in just a moment. But I need to keep going here. This becomes 7/3, and this becomes e to the third ln of e minus 1 to the third ln of 1 minus, this becomes 7/3 integral of just t squared dt. Okay, we have several moving parts now. I've already replaced the first part with the e. Now, natural log of e is just 1. Natural log of 1 is 0. So this whole part right here, that goes to 0. This part goes to 1. So we left to 7/3 e to the third minus 7/3. And this becomes 1/3 t to the third from 1 to e. So this gives us 7/3 e to the third minus 7/9 e to the third minus 1 to the third, which is just 1. And I guess we should clean that up a little. And I see like terms, we have e to the third, e to the third. So 7/3 minus 7/9 is 14 over 9. Seven ninths, and that is our answer. Now, believe it or not, all of that is just some decimal approximation. So we could actually multiply all that out. I'm not going to bother, but you could. And for our last one that we're going to be doing, number 5, we have the integral of x over square root of x to the 4th plus 16. And before I get going on this, I'm going to notice we don't have an x to the 4th. However, on our handout, we do have this here, which is going to be apropos to what we're doing in just a moment. Now, you'll notice our problem is x to the 4th. This is x squared. So we're going to have to actually adjust this, and we'll come back to that. I'm going to do a substitution, and I'm going to call it t for now. Actually, I can make it u. We're not doing integration by parts anywhere. So let u be x squared. And I want to point out that u squared is x to the 4th. So when I square both sides, I get x to the 4th. So that's going to be where that x to the 4th, I'm hoping, is going to become a u squared. Now, du is going to become 2x dx, which means 1/2 du is x dx. And that is going to be, turn into that. This is going to give me 1/2 the integral of 1 over u square root of u squared plus 16 du. Hopefully you can see all of that in there. And our rule that they gave us on the other page, just to be clear, says that the integral of 1 over the square root, instead of x, I'm going to use u just to make it simple, is the ln of the absolute value of u plus the square root of u squared plus a squared plus c. And once we get u, we're going to have to transform the whole thing back into x once we're all done. So this becomes 1/2, and this becomes the natural log of u plus the square root. Now, I want to point out that 16 is 4 squared, so a in this case is actually 4. So this becomes u squared plus 16 plus c. And we're going to transform that back into terms of x. U is x squared. And u squared is x to the 4th. I wrote that up there already. We have all of that. Now, you might be wondering, where did that formula come from? If you took a regular calculus class, that would be second semester calculus, you would learn where all of our rules, and you would learn many more new techniques as well. But for this course, this is all that we're going to need. Thanks.